Good morning, good afternoon, or good evening, wherever you are located in the world, and welcome along to the AMETEK Solid-State Controls webinar for the month of August. And this month we are going to discuss charger troubleshooting. We're going to have a general overview of how to troubleshoot a charger. So the first thing I always like to ask is, for everybody who's out there, if you can hear me, please type in the chat bar on the right hand side of the webinar room to let me know that you can hear me. And while I await those replies, I will go through some housekeeping. So first of all, my name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solid-State Controls. I'm located in the Stafford office down on the southwest side of Houston in Texas. I have over 20 years in the industrial UPS industry, working with many different manufacturers. Originally, I worked in the North Sea in the offshore oil and gas industry. And there will be a lag of around 30 seconds between you hearing my voice and me seeing a question. Basically, Webinar Jam is the platform that we use, and they've got to convert this signal into an Android signal, an iOS signal, and a Windows signal, and then send it out to all of you out there. So that takes a little bit of time to process. So basically, when I speak, you don't hear it until about 15 seconds after I've spoken. So therefore, if I say something and you ask a question on what I'm saying, I'm not going to see that question for about 15 to 20 seconds after I've said it. So what I tend to do is wait until the end of the webinar to answer any of the questions that were asked. And on the right-hand side of the chat bar, you'll see that there is a chat tab and a Q&A only tab. If you have questions, it would be much easier for me to go through them if you put them in the Q&A only section. So that would help me out tremendously, rather than put the questions in the chat if you put the questions in the Q&A only. The platform we use, Webinar Jam, has a panic button. So if we lose signal, or if I don't see any interaction, or it just seems like something has gone wrong, I can press the panic button. Webinar Jam will create a new room for everybody. It will invite us all in, and we will carry on from where we left off. Another popular question is, will the webinar be recorded? And yes, Webinar Jam does record the webinar, and if you registered for the webinar, you will be sent a link, and you will be able to view it pretty much immediately after the webinar has ended. And then what the problem with that is, when you press play on the Webinar Jam recording, it treats it like a webinar. In other words, you can't fast forward, rewind, and go to different parts as required. So what our fantastic marketing team does is they convert the Webinar Jam recording into an MP4, and then they upload that MP4 into our YouTube channel. That usually takes 24 hours for them to do that, and London has just posted the link in the chat, so that will take you to our YouTube channel. And if you follow that link, it will also take you to all of the other webinar recordings that we've done over the past couple of years. So if you want to go over some of the webinars we've done before, then you can do that. And you can share those videos with people by sharing the link. They are completely public, and you can do with them what you wish. And the last thing is, the webinar should last around about an hour with the Q&As at the end. Hopefully today we're not going to go over the hour, because I do understand that your time is precious and you can't spend a whole lot of time on your day listening to me waffle on about chargers. Okay, so everybody can hear me, and let's move on to what we're going to do today. So the objectives are to understand what a charger rectifier is, just a very quick overview. For more in-depth details, you can visit our YouTube channel by following that link that's on the page there. The webinar is called Understanding DC Chargers and Rectifiers, if you want more of an in-depth overview of how a charger works. We're going to discuss how to check input problems into a charger, how to check any transformer issues, how to check any semiconductor issues, either diodes or SCRs, mostly SCRs in our instance, how to check control board issues, and how to check any filter issues. Okay. So first of all, what is a rectifier? Very simple question to start off. Well, a rectifier is an electrical device that converts AC, alternating current, which obviously periodically reverses direction, to direct current, which flows in only one direction, so DC. There are two main types of rectification, and the one that we're going to deal with today is going to be full wave rectification. I actually took this slide off one of my previous presentations, and it shouldn't say there are two types of rectifications that we'll deal with today. The one that we're dealing with today is full wave rectification. And it's used in chargers to convert the mains AC supply, so AC power from your MCC, to DC power to charge batteries and supply any critical DC loads. And the main components of any charger system, not just an AMETEK solid-state control charger, but these are pertinent to ours, is you will have an input breaker, you will have a transformer, you'll have fuses, then you will have either a thyristor SCR diode bridge, then you have a control circuit, and then you have a filter circuit to smooth out the ripple DC into a nice smooth DC suitable for the battery system. So here is a basic charger with all of those components drawn. So you can see here we have our three-phase AC input right here. Excuse my drawing, my pen's not working very well. And then here you have a DC input breaker. I don't know why that pen's not working very well. And then that goes into a transformer there. Then we have our, oh goodness gracious. Then we have our fuses here. And then we have our SCRs, top and bottom here. And then this is the output of the system. Okay. We have our control board down here and some other parts of the circuits down there as well. So those are the main components on an AMETEK solid-state control charger. So the first thing that we're going to discuss is the AC input breaker. And you can see it highlighted on the screen there. Okay. And in our system, we take 480 volts AC in, and the breaker is opening and closing that 480 volts onto the primary of the transformer. And in truth, not much can go wrong with the breaker. Yes, mechanically, the contacts may not make, or it can get stuck in the on position, it can get stuck in the off position. But the main thing is, for AMETEK systems, when you apply power to the system, in other words, when you close that AC input breaker and 480 volts is available, the charger should start by itself. Okay, we don't have an on-off switch. We don't have an on-off push button. When the charger gets the AC supply that it's looking for, the charger will start to convert the AC into DC pretty much instantaneously. Okay, if that doesn't happen, then the first thing you want to do is check voltages both sides of the breaker. So if you have 480 volts A to B, B to C, and C to A on the input side of the breaker, then on the output side of the breaker, you're looking for 480 volts phase to phase. In this circumstance, it's wires 1 to 2, 2 to 3, and 3 to 1. Okay, if any of those phases are missing, that means that one of the contacts in the breaker is not closing correctly, and power is not getting to the transformer. And what you can also do is you can go to your MCC and isolate the power to the charger at the MCC if you think the breaker has a problem. And then without power, you can open and close that breaker and either meg or resistance check across each contact to see if one of them has an issue. Okay. Now, if you close the breaker and it trips instantaneously, or you go to the charger and the breaker has tripped, first of all, most people will think, okay, there is too much current flowing through the breaker and the breaker is tripped to protect the internal parts of the system. Yes, and in truth, that could be a possibility. But what I always like to tell people first is most manufacturers, and AMETEK solid-state controls in particular, we have methods to trip that breaker to protect the system for certain reasons. And on the page here that you can see, there's 3 boxes, and you can see the far bottom right-hand corner. You can see that there is this box here. That is a shunt trip relay that is connected to our control board. And in this circumstance, it's connected to the high voltage DC alarm. So basically, if the system sees high voltage DC at this point here, then it will actuate this relay. It will energize RLY1. When you energize RLY1, then that pulls in the contact for RLY1. And if you look, I know it's a little bit complicated to see in this drawing, but there is an auxiliary transformer secondary connected to the input transformer, and it's generating basically a 120 volt signal, and they're using it for fans and they're using it for other things. They're also using it for the control signal for this CB1 shunt trip coil. So if RLY1 closes, then CB1 shunt trip coil will energize. And if that energizes, that will trip the breaker here. Okay. So if we have high voltage DC on the output of the system here, then CB1 is going to trip. Okay. So if you find the breaker in a trip position, it could well be that the system is tripped on high voltage. And there are systems where you can also trip it for other reasons, whether it's high temperature or something like that. So what you need to do to test that theory is just remember, it's only a contact. So it's quite safe to pull RLY1. It will just be an ice cube relay, and that will prevent the CB1 shunt trip coil from actuating. So if you go into the system, pull RLY1, and then close the AC input breaker, if the AC input breaker remains closed, then you've ruled out CB1 as the issue. Then you know it's something external to CB1, whether it's a control signal or whether it's a high voltage circumstance on the output of a system. What we're trying to do is isolate any fault down to one thing. So if you remove RLY1 and it still trips, then what I would suggest is that you then go in and you remove the wires on the output of the breaker. So you would remove the wire here, you would remove the wire here, and you would remove the wire here. Lift it, tape it up, and then close the breaker again. And if the breaker remains closed, then you know there is something downstream of that breaker that is causing the issue. Okay. So that's the AC input breaker. Now I am going to use different drawings as we go through. They're all for AMETEK solid state controls drawings. Some are for our new digital charger, some are for our old analog charger. They're all pretty much the same. They're just drawn a little bit differently, and the control boards act a little bit different as well. So as you can see on the screen there, I've highlighted the transformer, and you can see that there's a primary and there is a secondary. So you can see that we have our primary here and we have our secondary here. And the primary is delta and the secondary is Y. Okay, and the transformer is an isolation transformer. So you can see on that drawing on the bottom right hand side of the screen there that the primary windings are not in any way, shape or form connected to the secondary windings. Okay, so they are completely isolated. There is no physical connection between the wires on the primary and the wires on the secondary. So it gives us isolation between the primary and the secondary supplies. Okay, and it also gives us a step up or a step down depending on what we require. And in our system, we usually step down the voltage. We're taking the 480 volts phase to phase on the primary, and we're stepping the secondary in this circumstance down to about 90 to 100 volts phase to phase, or 45 volts phase to the center point. Okay, so with that, on the primary, on the delta side, we don't use a neutral. So don't run a neutral to our chargers. If you're getting a new charger from us, all we need is 3 wires and ground, not 4 wires and ground. It's only 3 wires and ground. We just need phase to phase and a ground connection. We do not even have a terminal for you to run a neutral to our chargers. And our chargers are not phase rotation sensitive either. They do not care about the phase rotation of the input into the system. Okay. And also to be noted for the transformer is we do use auxiliary windings for things like fans and power supplies. And you can see on this drawing here that this winding is an auxiliary winding, and we've connected, a fan to it and some control circuits to that auxiliary winding. And excuse my drawing today because my pen seems to not be calibrated anymore. I will try my best as we go forward. So if the AC input breaker is tripping and you lifted the wires on the output side of the breaker and it stopped tripping, then it could be that there is something wrong with the transformer. So you have to be methodical and lift cables at the transformer. Okay, so obviously the first thing you would want to do is lift the cables going to each point of the transformer here. So that point there, and this point here. You'd want to lift the cables, take them up, close the breaker again, and see if the breaker tripped. That checks the wiring between the breaker and the transformer itself. So if the breaker stays closed when you have those cables lifted, then you now know that it could be something in the primary or the secondary of the transformer. And then at that point, you have to check the auxiliary windings, and you have to check the windings to ground. Now, remember, you can't check the windings themselves for a short, because a winding is just a coil of wire and it will show up as a short itself. Most faults are caused by a winding shorting down to ground. Okay, so just bear in mind whenever you're testing a transformer that if you go phase to phase, even with the power off, you're going to get pretty much a dead short. Okay. So the next part we're going to discuss is the SCRs, or thyristors. An SCR is a silicon controlled rectifier. It's a A semiconductor switch which has no moving parts whatsoever. That's why we use them, because with a switch, there would be contact bounce, they're not fast enough, and we want something that has no moving parts that is reliable, and that's why we use an SCR in charger systems. It is turned on by sending a signal to the gate of the device. Okay, and it's important to understand that you cannot turn the SCR off by removing the gate signal. If you remove the gate signal and there is still current flowing through the SCR and voltage across the anode cathode, then the SCR will stay on even though you've removed the signal from the gate. Okay, and it will only turn off when there is close to no current flowing through it. In other words, when there's no potential across the anode and cathode. And that, fortunately, happens every time a sine wave crosses the zero crossing point. At the zero crossing point, there is no potential between the anode and cathode. So if you remove the gate signal and allow the sine wave to cross the zero crossing point, then the SCR will switch off at that point. And the symptoms of a bad SCR include low output voltage, no output voltage, and blown fuses. Okay, that's the three main symptoms that you can see from faulty SCRs. Okay, so you can see on that screen there, I've boxed in the SCRs. Okay, and you can see them right here. That's an SCR, that's an SCR, and that's an SCR. And then also I've drawn in the fuses here as well. And the fuses we use are called semiconductor fuses. There's no semiconductor properties to the fuse whatsoever. All it is a fuse that's designed to blow so quickly it should protect a semiconductor from being damaged. That's what semiconductor fuse means. So if one of these fuses has blown, then the fault is always upstream of the fuse. Okay, something has happened upstream of the fuse. So in other words, something has happened in this box if a fuse has blown. With the power off, you can check the SCRs with the power off, and you can go between the anode and cathode. So for example, on this one here, you would go from this point here to this point here on a resistance on your fluke, and you should see an open, an OL, or a very high resistance on your fluke meter. And there's actually even a better way to do it. You can put one probe on the positive bus bar, and then you can put your other probe on A phase, then B phase, and then C phase, and then that tests all three. This pen is driving me wild. That tests all three of the SCRs there, and then move your fluke probe to the negative side of the output, and then you would do the same. You would go A phase, B phase, C phase, and that would check all three of these SCRs. Okay, you want to see, with the power off, you want to see OL or open on your fluke for good SCRs. If you see a short, then you can guarantee one of the fuses is blown. And when you see an SCR that is shorted, what happens is, so let's say, for example, this SCR here, it's shorted. In truth, that's not a problem until we switch one of the other SCRs on. So for example, when we switch this other SCR on here, then that would give us a path between basically this point here and this point here. So it would be a direct short across A and B phase. And that would cause either this fuse to blow or this fuse to blow. Okay. But when you're checking SCRs, you do have to remember about the transformer. The transformer winding is a short. So in truth, you have to bear that in mind because you will get a path with the transformer. So when you find out that there is an SCR short in the bridge, then what you actually have to go in and then do is, like, for example, in this one here, you'd have to disconnect that cable. You would have to disconnect that cable across the SCR and then check the SCR only taken away from the system to check each SCR individually to make sure that the one that you think is damaged is the one that's actually damaged before you replace it. And the way that an SCR works is basically, you can see the symbol, the circuit on the left-hand side here. We have our AC coming in at this point here, and then we have a lamp here, and then we have our SCR over here. And you can see that our gate signal is here, and you can see in each graph, this is a gate signal, this is a gate signal, and this is a gate signal, okay? And you can see the AC waveform on each of those graphs. And what the graph is actually showing you is, for example, on the top graph, we are turning the AC on, we are sending a gate signal right at the start of the AC sine wave for this system here. And once again here, you can see that dotted line is going up here, and it's getting turned on right at the start of the sine wave. Then obviously we have our zero crossing point, so that will switch off the SCR at that point there. And depending on where you fire the SCR in the circuit depends on how much of the sine wave gets through, which is what the other two waveforms are showing you. So in this circumstance, the top graph, this one here, will have the lamp shine very brightly, and this one down here will have the lamp shining much less brightly. So it's kind of like a dimmer is this circuit is showing you. Okay. And another test you can do if you have an oscilloscope available is you can check the output of the bridge. It's very important that you have to do it before the inductor, and you check it with a scope. So you can see, once again, this pen's going to drive me insane, but you can see our inductor here, and you have to connect your probe before the inductor, okay? Because if you do it after the inductor, then the capacitors will smooth out everything, and it will just be a DC signal that you see. And the important thing that you're looking for is this. For a three-phase fully controlled rectifier, you should have 6 pulses every 60 hertz, and 6 times 60 equals 360 hertz. And the other important thing is, on that screen for the oscilloscope that you can see there, all of the pulses are uniform. Okay, you can see that they repeat one after another after another. Everything looks symmetrical. Okay, so everything is good on this picture here. I'm not going to explain exactly what's going on, but that's roughly what the output of a three-phase full wave bridge rectifier output should look like when you look at it with an oscilloscope. Well, what shouldn't it look like? Well, you can see on the right-hand side here the oscilloscope trace, and you can see very quickly from the previous drawing that that's not symmetrical. There are points in that waveform that are missing. Oh, excuse me again. So you can see this point here, this point here, and this point here. There are pulses missing. And you can see the frequency. The frequency is now 60 hertz. Okay, so there is something wrong with this system. It's basically, we call it single phasing. It's that one of the SCRs or two of the SCRs are not firing. Okay, Now, a lot of people will think, okay, well, we must have a short. No, we probably don't have a short in this circumstance because an SCR is not firing. So that means one of the control signals going to the SCRs is bad, or the control system, the control circuit is sending a signal, but it's not getting to the SCR. Okay, hopefully I'll explain that in just a moment. So you can see in the box there, we have the control board. Okay, that is what sends the signals to our SCR. And in truth, it's very, very simple. How a charger works is you apply AC to the bridge, the control board turns on and says, okay, I'm going to switch my SCRs on. And then it uses a feedback circuit to say, okay, I'm going to look at the output of the charger and I'm going to adjust my voltage to make it what I want. That's pretty much as simple as it gets. So what the control board is doing is it's sending a signal on all of these outputs here. Okay, so I call them channels. So there are 6 channels for the 6 SCRs, and they go down to the gate signal of each SCR. You can see there's a gate signal there, and you can see the physical that there is the gate signal there going up to the control board. So for the SCRs to turn on, they have to receive a signal from the control board. So a very simple test that you can do with a fluke is you can check the gate signals using a fluke with the power on. So the charger has to be running, and you can check the gate signals, and they should all be roughly, for our systems, round about 1.5 volts DC. Okay, so the easiest way to check, let me do it, see if my pen is going to work. So on this circumstance, it would be this terminal here, I think that's 22, to this terminal here, 21. You want to check that, and it should be about 1.5 volts DC. Now, it is going to be a pulse train that it's sending. If you looked at it with an oscilloscope, it would be a pulse train of signals. But for ease, because most people don't have an oscilloscope, you're looking for just a voltage of around about 1.5 volts. And you have to check all 6 outputs of that system, okay? And what you're really looking for is they're all uniform. Like, let's say they are 1.7 volts. If 5 of them are 1.7 volts and one of them is 0.2 volts, then the one that's 0.2 volts is the one that has an issue. And if there is one that is low, then that tends to mean that the control board is not sending the signal correctly, and it is the control board that needs to be replaced. Now, there is a caveat to that. If there is something wrong with the SCR that could be pulling down that voltage, then it may be the SCR that's pulling down the voltage. So in that circumstance, you could lift the gate cathode signal going from the control board to the SCRs, and then check to see if the voltage of that channel on the control board changes. We're just trying to isolate where it is. Is it at the control board, or is it at the SCR? Also, you need to check the wires between the control board and the SCR themselves. Maybe a wire has been cut or nicked or has come loose. Check every terminal, make sure that all the screws are on the control board are tightened down. Make sure that the connector is seated correctly under that screw and hasn't been insulated from the board somehow. And then check where that cable is going to on the SCR and make sure it's going to the correct terminal on the SCR itself as well. Okay, and I think on this next one, you can see, so this is an SCR itself, okay, and you can see on the right-hand side that we have 2 terminals, and that's the gate cathode terminal, and we use push-on connectors similar to this to connect there. So we've seen examples where that connector has been pushed down between the plastic, so between this plastic bit here and the connector itself, so it's not making a good contact. It's not actually mounted on the connector itself, it's being pushed down between the connector. So that would give you an issue. Just be very careful. And there are some circumstances where internally within the SCR itself, the connection here is not physically connected to the internals of the SCR. The connection has broken. That's very difficult to tell. It's a very difficult test to find that. So in truth, all you're looking for when you suspect there's an SCR issue is that the terminals are connected correctly. Now, all control boards need to create a power supply, because all of the op amps, or even if it is a digital system that has a processor, they need a DC power supply to be able to operate. Now, some manufacturers might use an external power supply. I know on our DCR, our digital controlled rectifiers, we use an external power supply. But on our analog systems, which is what you see on this page, we are using the secondary of the three-phase input to step down our voltage to around 42 volts between 1 and 2, 2 and 3, and 3 and 1. And then that gets taken onto the board and is rectified using a small bridge rectified circuit and creates a power supply on the board itself. Now, if there is something wrong with that power supply, or if there's something wrong with the connections between the transformer and the board itself, then the power supply will not start up, and therefore the control board will not operate. Okay? So on most control boards, there will be an LED to tell you that the system is on. And you can see this is our analog board on the left-hand side. There is a square at the top there that's showing you a capacitor and an LED. And then on the right-hand side, you can see it zoomed in. You can see that red LED is called D3 and it says power on. If that red LED is on, then the control board should be sending out the signals as necessary. If it is off, then there is something wrong with the power supply on the board, or there is something wrong with the three-phase supply to the board. So you would have to go and check all of the voltages going to the board here. Okay. That light must be on for the charger to work. Now, not only does the control board use those three terminals to create a power supply, the control board also needs to know what the AC input sine wave looks like. It needs to know basically when the sine wave goes above the zero crossing point and when it goes below the zero crossing point. We call it the synchronization. And don't get it confused with the synchronization of a UPS. It just needs to know where the sine wave is in its cycle. Okay? So if the control board LED is on and the charger still doesn't seem to be producing an output, then you need to make sure the wires on the board go to the correct auxiliary windings, because the board needs to know the status of each phase to fire the SCRs. So if somebody had replaced the control board, for example, and they had mixed those wires up between 1, 2, 3, and 5, then in mixing those cables up, what's actually happening is it's difficult to explain, but let me see if I can break it down a little. So let's say this winding here is, so that's between 1 and 2. Oh, goodness me, this pen is driving me insane. So it should be looking across this winding here, and that should be in turn firing this SCR and the other SCR to return back to that system, to that point. So that's actually this SCR here. So the firing signals for those SCRs, so that comes from this one here, and this one comes from 25 and 26. So I think that is this one here. They have to be synchronized to that sine wave. So if they've been crossed somewhere, and for example, this SCR here is firing for a different phase, then no SCR is going to turn on because it's going to be unsynchronized. It's going to try and tell it to turn on at a point in the sine wave that is maybe negative anode to cathode when it should be positive. So you have to make sure that the synchronizing signals from the board match the transformer windings. It's very, very important. And then I mentioned earlier that the charger is as simple as AC in, control board sends signals to the SCRs to turn them on, and then it uses feedback to know what it is doing so it can regulate itself. And in this box here, you can see this is where the feedback is taken from, and it is wires 6 and 7 on the control board. So that is here. So you follow the wires down from there, and it goes to the positive of the system. So that's a positive there. And the negative of the system. That's this point here. So it's taking the positive and the negative onto the control board. So for example, in most of our charges, that's going to be around about 135 volts DC. So that charger is expecting to see a 135 volt DC signal going into the board there. If the voltage goes down, the SCRs will turn on more to make the voltage go back up again. If the voltage goes up, the SCRs will turn on less to allow the voltage to go down. It's a constant feedback loop that is happening all of the time. And what some people don't realize is if that feedback signal goes missing, the control board isn't clever enough to know that a wire has been disconnected or there's something wrong with the feedback circuit. If it sees 0 there, it thinks the output of the system is 0. So it's going to do everything it can to make that 0 turn into 135 volts. And to do that, it will turn the SCRs fully on. Okay? And in most circumstances, that will trigger a high voltage alarm and shut the system down. And in our system, that will trip the input breaker in most cases. Or there is also a backup on our charge control board. It's called the high voltage clamp. And it will actually, if it sees the voltage going above 145 volts DC, it will actually turn the charger, the firing signals off because it knows it shouldn't be up at that level. And the other thing that our systems have is a contact in series with the negative of the feedback circuit. And you can see the square there. It is highlighted as K304. Okay. And K304 coil is connected across A to B phase on the secondary of the power transformer. And basically what it's saying is, if I have AC power, K304 energizes, and therefore the contact for K304 closes. So if everything is good and we have power, this contact here should close and allow the feedback signal to get to the board. If we have a power failure, then K304 will open and feedback will not get to the board and it will shut the charger off. Okay. So that's what the feedback circuit is always doing. We have to make sure that the system has feedback going to the control board. But with that feedback, we have to know what we actually want the control board to do. We need to know what voltage we want. And on this system here, this is our analog charger. We need a float and equalize pot, because our charger both has a float and equalize, because we don't know what type of battery you're connected to. And if you have wet cells, then you want to be able to equalize them. So that circuit on the top left-hand corner that I've boxed in is where our float and equalize pot is. And here's it. It's a zoomed in picture of it. So K306, the contact K306, so you can see it at the top and the bottom. So K306, one set of contacts, and K306, the other set of contacts. Okay. So normally the contact is closed in the float position. And what happens is on pin 9 of the control board, that's here, we create around about a 10-volt DC signal, and we send it out this way here to the potentiometers on the board, but through the contact. And in normal float mode, this contact here for K306 is closed. So that allows the power to go through and down to the float pot. So there is our float pot there. Clockwise increases the voltage, counterclockwise decreases the voltage. And then whatever that voltage is set at, it will drop some amount of voltage, and then that set point will go into pin 10, which is our voltage threshold to the regulation circuit. So as that goes up or down, that adjusts the output of a system up or down. Okay. So if we have a fault here and there's 0 volts going back to pin 10 here, and that could be because we have a float pot that is open, or this contact has welded open, or there's a wiring issue somewhere. If we get 0 volts going back on pin 10 with respect to ground, okay, then the system thinks we want the output of the system to be 0. And therefore it will turn the SCRs off completely. So the default fail-safe position is if we have an open in our voltage threshold circuit, then we're going to get 0 volts out of the charger. So it's very important that that the regulation circuit works. And then if you flick the switch or push the button on the charger to turn it to equalize, then all that happens is this contact here opens and this contact here closes. And if that contact closes, then the voltage will go up and then down through here and down through this equalize resistor R032 back to the same point. So therefore you can see on our systems, the float and the equalize pot are completely independent of each other. You can adjust one and it will not affect the voltage of the other. Okay. So that's all that happens when we press the equalize button, is the contacts for K306 change, that will close, and that means we are using this resistor instead of this resistor. It all goes back to the same point, which is pin 10. Okay. Now, I mentioned feedback earlier, and I was specifically mentioning voltage feedback, but we also have current feedback, and you can see it highlighted on the page there. And in this system, it's terminals 13 and 14. And in that highlighted box is what's called a shunt. And a shunt is just a precision resistor. If you need more information about shunt, go back to our webinar on charger the in-depth charger webinar, and it will show you what a shunt is and how it operates. But basically what it's doing is it's measuring the current flowing through it by dropping a voltage across it. Okay, so our control board works for all types of chargers. It could be a 50 amp charger, 100 amp charger, 150 amp charger. The control board really doesn't care. Okay, and therefore if we have a 50 amp charger, the SCRs that we use on there are going to be much smaller than, for example, a 500 amp charger, where we're going to have much bigger SCRs. And we need to protect those SCRs. So let's say in our 50 amp charger, our SCRs that we use are rated, just let's say for 100 amps. We have to make sure that the current flowing through those SCRs never ever gets above 100 amps, because that could destroy the SCR. That is what the current feedback circuit is trying to do. It's trying to make sure that the current does not go above the current that would damage the SCRs. So therefore, there is a potentiometer on the charger control board that we set to set that current limit. And what will happen is, in that example that I just said, if we set the current limit at 100 amps, then therefore what happens when 100 amps starts flowing out of the charger, then the control board will start to regulate the voltage. It will lower the voltage of the charger to keep the current at 100 amps. If necessary, it will phase the charger completely off, as long as the current doesn't go above 100 amps. So that is what that circuit is doing. So if there is a problem in the current sensing circuit, then that could cause a low voltage scenario. So for example, let's say that the current limit pot on the charge control board is set too low accidentally. Somebody has been messing around with it, didn't know what they were doing, and they've set the current limit, let's say at 20 amps. If that charger then tries to supply more than 20 amps, the voltage will start to go down to maintain no more than 20 amps of current. So if you see a low voltage on a system, don't automatically assume that it's because the float pot has been set incorrectly. It could be that the system is in current limit. So pay attention to that when you go and see a system. And then the last part we're going to talk about is the filtering side. So DC electrolytic caps are designed to fail open when they fail in a controlled way. They have a valve on them, and the interior design is that pressure builds up, and if it gets too much, the lid will pop, and that will disconnect the internal of the capacitor from the terminals, and it should fail open. Unfortunately, it doesn't always work that way, and they will, if they fail short very quickly, they tend to fail catastrophically, which means they blow themselves apart. Smoke comes out of them. It's very obvious to see physically a failed capacitor. Okay, so there are some circumstances where it can fail low resistance and cause issues, but it's very, very rare. So when you're checking capacitors, the first thing you need to do is physically look at them, and if anything seems damaged, then you have a problem. The other thing that you can do is you can measure across the capacitors with a fluke, and I don't know what that measurement is going to be. It depends how many capacitors you have in parallel and what value the resistor, the dissipating resistor is across those capacitors. But what you want to see is the resistance will start low, and it will start to gradually build up as you keep your probes on the output of the capacitors, on the positive and negative of capacitors. So if you put positive and negative of the capacitors and you don't see that resistance gradually ramping up, then it would tend to be that there's an issue with those capacitors. It's a very simple test. The other part of the filter circuit is a choke or an inductor. and I've highlighted the choke inductor on the screen there. And they very, very rarely fail. In truth, I don't think I've ever found a choke or an inductor that's failed, because it's just a coil of wire like a transformer. And the worst case scenario is that they will fail open, which prevents the charger output voltage getting to the output breaker. But in most cases, because it's a short, even if it's a winding to winding short inside a choke, that's not going to really cause any issues. It's just going to increase the ripple that's seen out of the system. So it's very rare for a choke to fail, to be perfectly honest. Okay, that is the end of the presentation today. Hopefully, you've gained some information on how to troubleshoot a charger. If you have any questions that were raised during that presentation, please let me know in the Q&A or in the chat while I go over the housekeeping of saying goodbye to everybody. We've got about 5 minutes left, so if you have any questions whatsoever, let me know. Okay. So I would like to take this opportunity to thank everybody for attending the webinar today. Hopefully it gave you some insight into how a charger operates. It's a relatively easy circuit, and if you follow the troubleshooting and the circuit diagram, then you should be able to figure out most issues with the charger. Obviously, I couldn't go into real in-depth troubleshooting that an AMETEK FSC would do when they come out to site. It's just too big of a subject to cover for one webinar, but that gives you an overview of the basic things to check in a charger. Taylor has asked, will the video be available for viewing at a later time? Yes, you will receive a link from Webinar Jam and you can watch it as a webinar, or if you look down, you can see London has posted our YouTube channel, and if she posts it again, that would be good. You can go to our YouTube channel and you can see this and every other webinar that we have created. It takes the marketing department 24 hours to convert it into a YouTube file, so please give them 24 hours, but you can visit the YouTube site and watch any of our videos. Also, if you have any other questions or concerns, you can contact us directly using our webpage or using our email address. London will also post that into the chat bar. We respond to all of the emails and all of the requests as quick as we can, depending on how busy we are, but every single one does get replied to. Thank you, London, for putting it in there. We do have a question that's come in. They're saying that we are experiencing AC fail alarms, but we are not losing AC. Where would one start to troubleshoot this? Ooh, that's a difficult question. Basically, you've got to look at that at the point of view of the system itself. So if it sees that you are getting an AC fail, it thinks that you are getting an AC fail. So it says that you're not losing AC. Are you putting a power quality analyzer onto the AC into that system and seeing how low the AC voltage is dipping, if it's dipping at all? That's the first thing I would do, because most charger manufacturers will have an AC fail alarm come in at probably more than 10% plus or minus of the system. I think ours is more like down at 400 volts for a 480 volt system, so it's about 20%. But you know, you need to make sure that your AC isn't dipping when you're getting these AC fail alarms. And if you rule that out, then pretty much it's either going to be the control board that's monitoring the AC is faulty, or it is the cabling between where it measures the AC voltage to the control board. There could be a loose connection between there. So that's the three things I would check. First of all, make sure you're not having an actual AC occurrence. then check the wiring between the transformer and where it lands on the control board. And then if that doesn't point to anything, then you would probably need to replace your control board if the control board is where the AC fail alarm is being monitored. It says that you've put a power quality meter on for 48 hours without a flicker. The alarm is ringing 4 to 6 times per hour. The other question then, Kevin, is the alarm showing up on the charger, or is it only showing up on your DCS system? So if it is showing up on the charger, you do what I said, check the cables and then change the control board. If it's not showing up on the charger, but it's showing up on your DCS system, then it could be a problem with the relay that operates that alarm or the cabling between your charger and the DCS system. Hopefully that helps you a little bit. I can't see any other questions or questions or comments that have come in. So that is 11 o'clock here in Texas. So that's 1 hour exactly. I'd like to thank you very much for taking an hour out of your day to listen to me ramble on about charger and charger troubleshooting. You will receive a survey when this webinar is complete. Please, I think it's question 5 asks what topics you would like to be discussed in the next webinar. I read every single one of those, and I'm really interested to hear what topics you want covered. Because in truth, I've been doing this for nearly 2.5 years now, so I am running out of topics. So if you could let me know what you want me to discuss at our next webinar, I would truly appreciate it. So until then, that's going to be a month from now. Take care, enjoy the rest of your Wednesday, and thank you very much for attending this webinar today. Take care, and I'll speak to you soon.